Hello and welcome to this the 13th class in our physics of materials lecture series. So, in all our classes so far we have already travelled quite some distance in the general area of this subject. We have successfully built one model for the materials, especially trying to explain the electronic properties as well as the thermal properties, and that model was the Drude model. We were able to build the model, we were able to check whether this model is good in explaining all the properties that we see of the materials, and we found that in fact it was good in some respects, but it also had some shortcomings, specifically with respect to specific heat and the average translational kinetic energy of the electrons. So, we have travelled quite some distance in that sense, in the sense that we have actually gone through one model and examined its capabilities. Having come that far, we went even further. We said that to improve upon what we have already done, we need to examine our existing model to see what is the source of that shortcoming. So, it is not enough that we know that the model is limited in some ways. We would like to have a better feel for why is it limited in those aspects. So, in that context we examined the fact that the Drude model has effectively used the Maxwell-Boltzmann statistics in describing the electrons, and that is itself a piece of information that we have picked up from the fact that the kinetic theory of gases actually uses the Maxwell-Boltzmann statistics. And since we have effectively just extended the kinetic theory to the metal, the electrons are also effectively believed to be using Maxwell-Boltzmann statistics within the framework of the Drude model. So, in the last class we went through the exercise of deriving the Maxwell-Boltzmann statistics. At that stage we specifically did this process, one to of course understand how this kind of a statistical process is employed to handle a range of particles and the kinds of particles and conditions that we are trying to handle. So, that itself is a very useful exercise to have, because that is the kind of exercise you would have to go through if you were trying to extend this kind of a learning process to some other new system that you are trying to examine. So, therefore, in that context we have looked at this the derivation of Maxwell-Boltzmann statistics. But more specifically we also wanted to see what is it, how is it that you will handle a set of particles with a certain set of characteristics, and how you can translate that to statistical information that can then be used. The reason we did this is we would also like to use a similar process, though not exactly identical, but a similar process if we were to actually put different characteristics for those particles. Okay. So, therefore, understanding how it is done in one case is very useful, so that we can make the appropriate changes if we were to try and do the same process with a slightly different set of rules that we are expecting the particles to behave or obey. So, it is in this context that we have derived the Maxwell-Boltzmann statistics. So, to briefly restate what we did in the Maxwell-Boltzmann statistics, we came up with a final expression that looked like this. Okay. So, where Ni is the number of particles which are sitting at the energy level Ei, okay, and N is your total number of particles. P happens to be something that we described as the partition function, which is essentially the sum of all these terms over all the Ei of just this term here, term that we see out here. Okay. So, that is what this works out to. So, if we make a plot of this, which we did last class, so we will start with that plot and proceed. So, we will see a plot that looks where we have essentially the energy levels increasing that way, and this is the number of particles. Okay. So we have these are the two parameters that we wish to plot against each other. We see a plot that looks something like this, where the way we read this plot is, this is energy level E0 and that has n0 number of particles. If you take an energy level E1, it has n1 level n1 number of particles, E2 n2 particles, E3 n3 particles, and so on. And so you have some energy level ER nr number of particles. So this is the way we would read this graph, the way we would read any other graph also, but essentially this is how the two pieces of information that we are trying to correlate end up showing up in a graph. And if you, as you can see from this expression that we have put down, as the energy level goes up, the number of particles is going to come down, because it is minus EI by kBT that we have up there. Okay, so in general, as the energy level goes up, the number of particles at that energy level occupying that energy level will come down, which is basically what you see here. This is increasing energy here. So as you go up and up in energy, the number of particles occupying that energy level is actually coming down. Okay, so this is the information that we have. We can also make a slightly this is at one particular temperature. Okay, so when we make this plot, in this expression n is a constant, and this partition function will be a constant because we have a fixed temperature, and this particular temperature is a constant. Okay, so now supposing we were to do this at some other temperature, then what is it that we would see? You can we will make the same plot here. So this is number of particles, and this is energy levels. So without going into much detail of all the particles that we just saw, we will just have two curves that look like this. This is at T1 and this is at T2, where T2 is greater than T1. Okay. So what this basically means is that as the temperature goes up, in this case T2 is greater than T1, the higher energy levels here will have more parts. So at any given energy level, so let us say whatever, I will just arbitrarily say E10, okay, and this is still E0, this is just arbitrarily chosen as E10. At E10, which is a high energy level, originally we had a certain number of particles, now we actually have a larger number of particles. Okay, so at a higher energy level, some arbitrary level E10, originally we had some number of particles, now we actually have a larger number of particles. So the higher energy level is actually getting more populated, is more heavily populated at this in this temperature condition. If you go to a low at a lower energy level, such as in fact even E0, at E0 originally it was this many number of particles, now at a higher temperature it is lower number of particles. Okay, so what is happening is, as you raise the temperature, lower energy levels are getting less populated and the higher energy levels are getting more populated. And this makes sense overall, because first of all the number of particles is fixed, so you cannot arbitrarily raise the number of particles at some energy level without making any difference to the number of particles at the other energy levels. Okay, so in general number of particles is conserved, so therefore if it at all goes up at some energy level, at some other energy level the number of particles has to come down. So that part is correct, that part is consistent with what we are dealing with, but at the same time the overall energy level of the system is going up. When we say temperature is going up, that is basically what we mean. When temperature has gone up, the energy level associated with that entire system has gone up. So which means the total energy of the system has to go up, which means the sum of the energies of all the individual particles, that sum has to go up. For that sum to go up, the number of particles at the lower energy level comes down, so the contribution of the lower energy levels decreases, but the contribution of the higher energy levels increases, and therefore the sum actually goes up, and that is why that is how the overall energy of the system goes up. So so this is the picture of this system that is following Maxwell-Boltzmann statistics and how that system behaves as you change the temperature. Specifically in this case we are raising it from T1 to T2. Now when we spoke about the limitation of the Drude model, one of the things that we said is that it does an incorrect prediction of the electronic contribution to specific heat. Okay. So in fact it is over predicting the electronic contribution to specific heat. Now if you see here, this diagram that I have drawn here is actually showing you the difference in energy, the difference in the layout of energy in the system as a function of temperature. Now when we talk of specific heat, that is essentially what you are talking about. At specific heat is simply that if you have some temperature for the system, you would like to know how much energy you have to provide to that system to raise the temperature of that system by some small delta amount, small delta T. So I have arbitrarily chosen some T2 which may not be a small delta T higher than T1, but it still encapsulates this information. This information is in some ways related to the, is in fact directly related to the specific heat of the system, because that is actually also capturing the same information, except it is giving it to you in some specific units. Here we have put it down in a graph, right. So so when we say that the electronic contribution of specific heat is not being accurately predicted by the Drude model and therefore by the Maxwell-Boltzmann statistics which is hidden within the Drude model, or in fact is the basis of the Drude model, what we are actually saying is that this kind of a change in distribution of energy levels and the number of particles at those energy levels, this kind of a change in distribution as predicted by the Maxwell-Boltzmann statistics is not valid or does not appear to be valid for electrons which are present in a solid. Okay. So that is the basic information that we are gathering, or the kind of idea that we are forced to consider, because this is what the information is and this is where the error is, right. So so we now see that we have by coming up with this Maxwell, by looking at Maxwell-Boltzmann statistics in greater detail, we have actually been able to get very close to where is it that we are having an issue with this derivation, and as a result of which this model is having some problem making some predictions, right. So this is the crux of the problem that we face. Now having come this far, let us probe this issue a little further and see this graph has not come arbitrarily, right. This graph has come because we assumed that the particles had certain characteristics, that they followed certain rules. Only because we made that assumption, we were actually able to develop the rest of the statistics. That statistics is based entirely on those assumptions, right. So and in this case the assumption that is of significance is the assumption that impacts the manner in which we count the states, the manner in which we count the states, the manner in which we figure out what is sitting in which state, whether to count it as one state or two states and so on. So that is very integral to what we are talking of when we say a Maxwell-Boltzmann statistical distribution. Okay. So somewhere there in those rules that we made, saying that our electrons in the solid follow those rules, somewhere there we have made an error. So that is where the issue is. Now the specific aspect of the Maxwell-Boltzmann statistic that stands out, which is very fundamental to why this graph ends up this way, is that we have said that those particles are identical and distinguishable. Okay. We have said that the particles that are classical particles, we have used all those terms. We have said classical particles is a term we have used, we have said identical particles, we have said distinguishable particles. These are all terms that we have used, and any physics book you take or any solid state physics book you take, you will find some mention of these words. Classical is a word that you will see, identical is a word you will see, and distinguishable is a word you will see. So we have assumed this, and we have also, like I said, mentioned that these are classical. So fundamental to Maxwell-Boltzmann distribution is the fact that we assume that the particles are classical and that therefore they are identical and distinguishable. So so this is the combination. So in today's class we will actually spend we will try and examine this combination very carefully. What we mean by saying classical, what do we mean by saying classical means identical and distinguishable, and so on. I also want to state this, that for the longest time, I mean one of the reasons why we use this kind of terminology, especially with respect to classical, is that for the longest time this is all we knew. For the longest time, all the particles that we examined at all levels, including large particles, which I mean, and large objects and so on, were all considered classical. We did not know any different. We were not aware that there was a possibility that we could consider them in any other manner. Okay, only around the year 1900 did the idea come up that you could actually consider them in a somewhat different manner, and that it is possible that they may be behaving in a different manner, and that there are specific circumstances under which we get closer to when it is necessary to in fact think that they do not behave this way. Okay, so all those things came up only around the year 1900. So all of the sort of the old physics that if you wish to say, the way when you say Newton's laws of motion and so on, those were all described assuming that the particles are classical. Okay, so all those things are true, and as we examine this further, I would like you to keep that in mind, so that when you go back and look at any old notes you have on Newton's laws of motion and all the other things that you may have done in physics, you can reassess everything that you have learned, or re-examine everything that you have learned from the perspective of this idea that much of what was described was pertaining to something that is classical, and therefore even the physics is then called classical physics. Okay, so this is the thing. So now we will look at identical and distinguishable. So these are the terms that we will look at, and we will see what we mean by it. So first of all, we say identical. Now when do we say something is identical, or when do we say something is not identical? This is the first question we will ask ourselves. The simplest way, I mean, when we say something is not identical, when we say two objects are not identical to each other, it means we are able to clearly demarcate which is one object and which is the other object. Okay, the simplest way we do that is simply to look at the properties of that properties or attributes of properties or attributes of the object. So you just look at properties or attributes of the object. If they are not the same, they are obviously two different objects, and you are able to say so convincingly. So to assist us in this process, I'm just going to show you. I just brought along a few plastic balls, toys that you can easily find anywhere else, and I'm going to pick up some of them and show you use them as examples to assist us in this discussion. Okay, so I'll randomly pick up a couple of them, and then we will see what we can say about them. Alright, so we now have I now have two balls, two plastic balls which you could get anywhere in my hand, and as you can see, they are essentially more or less the same size. In fact, in this case they happen to be the same size within experimental error, and but clearly they are not identical, right. So in this case the color is the distinguishing factor. It is very easy for us to distinguish between these two. They are large scale objects, they are not small objects. We have two different ones, very easy to handle in your hand, and they are not the same. Okay, so this is definitely not identical. So when we say that we are able to distinguish between them, there is no issue here. These are not identical and they are distinguishable. So this is what we have here. We could also consider another combination here. So in that case the sizes were the same, but the colors were not the same. In this case the neither the size is the same nor is the color the same, right. I have a pink ball in my left hand and a green small ball in the right hand. So it is easy for us to now differentiate between these two, because neither the color is the same nor the size is the same, right. So in what is called the classical physics, this is the manner in which we go about things. These are anyway not there is enough that is different about these two that we have no issues demarcating between them, right. So this is how it goes on. I will take two more here. Now these are exactly the same size, again with an experimental error, these are exactly the same size and they are also the same color, alright. So in our kind of a discussion, it is this scenario that is of significance to us, that we have actually two objects which have all their attributes being the same in terms of, in this case, the color and the size, and if presumably the weight and so on, because it is the same material. So we have the same two objects. So in classical physics, what we say is that even when you have two objects like this, you can actually distinguish between them, meaning I can say that this is in my right hand and I can say this is in my left hand, and I can say with confidence that they remain this way, right, as long as I keep them this way, as long as I do not consciously interchange them. This is the one, this is the ball that is in my right hand and this is the one that is in my left hand. So I am able to confidently distinguish between the two of them. This may not immediately sound like a very significant statement, but we will look at an alternate condition and then we will find what is the significance of the statement that I made. Okay, so we will just hold this for the moment, we will get back to this in just a moment. Now if you look at the atomic particles, so to speak, atomic and subatomic particles, what do we have? We have atoms, we have protons, we have neutrons, and we have electrons. Now if you look at the size scale that we associate with some of these, this is of the order of an angstrom. Okay, so that is roughly 10 power minus 10 meters. Okay, so an atom is roughly about 10 power minus 10 meters. In fact, incidentally, the typical interatomic space is about twice this, of the order of 2 angstroms. This typical interatomic distance that you can talk of in a, if you want a generic number that you want to work with in terms of interatomic distance, this is the number you would work with, 2 angstroms, of which each atom is about an angstrom. So that is what we are looking at. Protons and neutrons are believed to be of the order of 10 power minus 15 meters. So they are estimated at 10 power minus 15 meters is the size scale that you associate with a proton or a neutron. So that is already 5 orders of magnitude less than what we associate with the entire atom. Okay, so that is a very small number. So in fact if you look at okay, so this is something that that we are looking at 10 power minus 15 meters, we will elaborate on that a little bit. If you look at electrons, the estimates are that it is less than 10 power minus 18 meters. Okay, so that is a very small number, 10 power minus 18 meters is a very small number. It is less than that, that is just an estimate of what it is. Exact numbers are I believe very difficult to get, but that is the kind of estimate that we have for the general sizes of the atomic and subatomic particles that we conventionally deal with. If you look at the best materials characterization techniques, they are getting into the 1 angstrom and sub angstrom size scales, but you will be really hard pressed to actually look at individual electrons and so on. So this is going to be this is a odd, I mean, so when we are talking of size scales, this is a significant drop. When you go from 10 power minus 10 to 10 power minus 15 or 10 power minus 18, this is like a huge drop in size scale that we are talking of. Okay, so we are actually looking at objects of this size scale. Now in real life, when I picked up 2 orange balls here and showed it to you, this is completely different size scale. We are talking of the order of say 5 centimeters. Okay, so 10 power minus 2 meters is the kind of size scale that we 10 power minus 1 to 10 power minus 2 meters is what we are talking of. So that is actually about almost 8 to 9 orders of magnitude higher than this, and about virtually 10 power is of the order of 16 orders of magnitude higher than what you have here. Okay, so this is one of the issues that we have to become aware of when we are talking of objects of different size scales. Okay, that first of all we should be conscious of the fact that we are actually dealing with objects of different size scale. The reason I point this out is that some of the things that we talk of conventionally in physics, in fact if you talk of when people say Newtonian physics and so on, the the reason many of the things, many of the theories in the past have held well with all of that has been described using Newtonian physics is because typically all of the objects that were described were all large scale objects. Okay, so large scale in this sense. So when we talk of if you look at any problem, I mean if you really look at a physics textbook that talks of a billiard ball hitting another billiard ball with such and such velocity arriving at such and such speed, or a projectile being thrown at some particular velocity and some particular angle that is described to you, and so on, they are all large scale objects. Okay, so in that sense, and it turns out that many of the things that we say of large scale objects is therefore it works out to be very valid for those objects. As you go to smaller and smaller size scales, and this is the size scales that we are talking of, it turns out that some of the things that we are saying is not it is not possible for us to say the exact same thing with the same level of certainty when we go down to smaller and smaller objects. So this is one issue that begins to crop up. Okay, so this is something that we need to be aware of, but we will examine it further as we try and discuss this in a little greater detail. Now clearly when I spoke about these various examples of a green color, a small green ball versus a big pink ball and so on, obviously it is possible for us to distinguish between an electron and a proton, an electron and a neutron, an electron and an atom, similarly a proton versus an atom and so on, simply because they are of completely different size scale, right. So being able to distinguish between these various particles is quite straightforward because their size scales are very different, except of course the proton and neutron combination. Here the size scale is the same, but the charge is different. It is the same as saying that I had a pink colored ball and an orange colored ball. Size scale is exactly the same, but the color is different there. So another attribute of the ball is different, and therefore you are able to distinguish between the two of them. In this case, the attribute of the particle that is different happens to be the charge. Okay, so you could have charge of the particle, you could have mass of the particle. So we'll just put those down. So primarily charge and mass. Okay. So for our purpose these are the two that we will look at, charge and mass, and charge and mass to the extent that and therefore the size scale, like if you want the size of that particle by looking at protons, electrons, neutrons and the atom and a single atom, we find that between them either the charge is different or the size is different or the mass is different or more than one of them is different, and therefore you can distinguish between them, right. So therefore in this discussion that we have had, we are able to extend to an atomic level and look at ways in which we are able to identify independent non-identical particles. It is very easy to differentiate between non-identical particles because they have enough of an attribute that is different. Now the question of importance to us, we are this entire discussion is at some level eventually going to apply to a bunch of electrons in a solid. Okay, so that is the direction in which we are headed. Now when we talk of a bunch of electrons in a solid, the issue with respect to these attributes of particles that immediately stands out is the fact that amongst electrons their attributes are the same. Okay, so when I take two electrons and you compare them, then you find that their charge is the same, their mass is the same, their size is the same, right. So those three are the three attributes that we are looking at in this case, the charge, the mass and the size are the same. That is why we are able to specifically ask, when you look up a reference book, it will give you a mass of an electron 10 power minus 31 kilograms. Okay, so so that is you get as a mass of an electron. You can get 1.6 into 10 power minus 19 coulombs for the charge of an electron. So these are some standards, so you can find these standards. Okay, so therefore their attributes are now the same. So the question is, if you have two electrons, can you distinguish between them? So that is what the question is. So we have, so in other words, the attributes being the same of the two particles being the same, when you have such a situation, we describe that by saying that those two particles are identical. okay. So the word identical in our general discussion of identical versus distinguishable and so on, the word identical in our context is being used to capture the information that the attributes of the two particles are the same, the mass is the same, the charge is the same, the size scale of that particle is the same, so therefore those two particles are identical. Now the question is, given that you have two identical particles, can you distinguish between them, okay. So it goes back to this idea that I just started off with, which is that I have two orange balls where essentially their attributes are the same, their mass is the same, in this case if you want to say the color is the same, and to the extent that they are charge neutral at this point, their charge is also the same, their size scale is the same, everything is same about these two plastic balls that I have in my hand. So therefore they are identical, attribute wise they are identical, and I wish to know whether I can distinguish between them. In this case at this size scale which is of the order of 10 power minus 2 to 10 power minus 1 centimeter, sorry 10 power minus 1 meters, in this size scale I am able to distinguish them simply because I know for a fact that I am holding one in my right hand and one in my left hand, and they remain that way. I have no confusion on this aspect, I have no reason to believe that they have in any manner changed their positions, that I have control on where they are and how they are positioned, okay. So therefore I am able to distinguish between them at this size scale. So these are identical but distinguishable at this size scale, that we are dealing with. Now we wish to know that if you have two electrons which are now having all the attributes being the same in just the same manner that we had of these two plastic balls, and we are essentially talking of a very small size scale, less than 10 power minus 18 meters. If you are getting down to that kind of size scale and you have two electrons, are they identical and distinguishable? Can I say for a fact that I have control on exactly which is electron, the first electron that came into the system, and where is the second electron? So this is the issue that we have. What happens is that upfront we do not know the answer to this question, alright. So the question has been posed, I posed the question that these are two identical particles, can you distinguish between them? So upfront we do not have an answer to the question. The way we go about it is we assume an answer and we check whether it is correct or not, alright. So when we look at classical mechanics, which is what I have mentioned all along, the assumption that we make for the two electrons is the same assumption that we make for the two plastic balls that I showed you. So the two plastic balls which are at the size scale of 10 power minus 1 meters, I am able to say with confidence that even though they are identical, I am able to distinguish between the two of them, okay. So in other words, if I keep one ball up and one ball down and I swap them around, I can say that the second ball only has gone up, okay. So I am able to confidently say that which ball has gone up, which ball has gone down, I am able to confidently say. In relevance with respect to the kind of system and the kind of problems that we are trying to discuss, the concept of interest for us is the trajectory. Okay. So the concept of interest to us is the trajectory of the particle. I just mentioned to you another concept of interest, which is the position of the particle. So I just said that you could have two different orange balls and I could keep one up, one down, right. So I have two different positions for these two orange balls. I am able to say that if I swap them around and the ball in the left hand has gone up, the ball in the right hand has come down, I am able to say that I know this for a fact that whatever was in my left hand only has gone up, whatever is in my right hand only has come down, okay. So this is a new position with a different ball on top and a different ball at the bottom. So this is what we mean by the fact that they are identical but distinguishable. With respect to the particles and the kind of situation in which we are examining them, which is that these particles may be electrons or atoms. If it were a kinetic theory of gases, they would be gas atoms or gas molecules, and if it is electrons in a solid, they are electrons. They are all randomly moving around, alright. So this is something that we discussed already. So that they are randomly moving around, they are bouncing off of each other, they bounce off the walls of the container they are in, and so on. So at that point the additional attribute of the particle is its trajectory, okay. So so one particle is moving in some direction, another particle is moving in some direction, it may be that their trajectories intersect, so they hit each other and they bounce off, right. So all these things could occur in a system consisting of particles kept at some energy level where they are moving around randomly. they could hit each other, they could hit the walls of the container and so on. So this is a ongoing process in that kind of a system. So now our question of interest is that with respect to the trajectory of those particles, can you distinguish between the particles? Okay, just the way I said that with respect to the position, I was able to distinguish between those two particles. I could move them up and down, and I could say with confidence which is the particle that is up, which is the particle that is down, even though all their attributes are exactly the same, right. So now with respect to trajectory, what we mean is that, you know, if let us say the two balls come, they collide and they move away, right. For this kind of a problem, you can take the Newtonian approach, you can say, you know, energy is conserved and so on, and you can write equations which show you that you have an initial path for this ball, you have an initial path for the other ball, you can predict exactly when they will collide, and at the end of the collision you can say that, you know, if energy is conserved and so on, you can say in which direction will the ball on the right side move, which direction will the ball on the left side move, right. So you can clearly predict the approach of the two balls, predict the fact that they collide, predict the fact that they will move away, and on top of it you can predict clearly not just the positions of the two balls, but I could have marked one as A and the other as B. I can tell you exactly where A will be at the end of the collision, exactly where B will be at the end of the collision, and there will be no confusion in it, right. So we would like to know that with a bunch of electrons, can we extend the same kind of an argument. In other words, if you know the trajectory of the electrons, if you have a bunch of electrons and you take two of those electrons and you know which is the path in which one of those electrons is moving, which is the path in which the other electron is moving, and let us say for example that they collide, just for the purpose of our discussion, let us say they collide and they move on. We would like to know for a fact whether or not we can say that the electron that was, let us say, on the left side has gone to a particular position and the electron that was on the right side has gone to a particular position. So that is what we mean by saying the fact that they are identical because their attributes are identical, but they are distinguishable because I can keep track of an individual electron with confidence that it is that very same electron, right. So now when we talk of classical physics and we extend the principles of classical physics to electrons in a solid, we are extending this idea that the two balls can be distinguished from each other, which is valid at this size scale, to two electrons which are present in a solid. So we are saying that two electrons are identical because their attributes are the same, but by keeping track of their trajectory you can uniquely identify a given electron at all points in time. That is what we mean by saying that the electron is identical but distinguishable. So classical physics uses that line, it says all electrons or any particle that is a classical particle is identical, even if it is identical, is still distinguishable based on its trajectory. Okay, so if you know the trajectory of the particle, you can say for a fact that that is the specific electron that you are following throughout your discussion. Okay, so that is the thing. So when we talk of classical particles, this is all this is true, and we are also saying that as long as you keep track of the trajectory of the particle, you can uniquely identify the particle. Fine. So now till about 1900, this is all that we were aware of till the year 1900, and all the discussions that people had about various particles on various objects and so on, and calculations that people made on systems were all based on this basic assumption, and therefore were all based on the Maxwell-Boltzmann statistics, because the Maxwell-Boltzmann statistics actually say effectively assumes this, right. In what form does the Maxwell-Boltzmann statistics assume it? It basically says that, you know, if you have for example two energy levels, right. So two energy levels, again if you look at it, in this case the up down analogy is useful for us. Two energy levels, I have an energy level, a higher energy level and a lower energy level. I have a particle at the higher energy level, a particle at the lower energy level, and these two particles are identical particles, alright, they are identical particles. Supposing I swap, so I count this as one state, the system is in one particular state when this particle is up here, this other particle is down here. Supposing I switch them around, based on classical understanding of the particles, the classical theory of the particles, since I am able to distinguish between the particles, since I can say with confidence that this is a different particle and this is a different particle, since I can say that with confidence, this new arrangement is a new arrangement, it is not the same as the old arrangement, I have swapped the particles, right, and this counts as a second arrangement. So in classical physics this is one arrangement and this is another arrangement. Okay, so these, even though you have two particles having the same energy levels, so to speak, occupying similar energy levels. Now around the year 1900 and beyond, we stumbled upon, thanks to famous people whom we will like Max Planck and this is something that we will discuss in great detail in the next couple of classes, thanks to a bunch of people who did a lot of interesting work in the early from the year 1900 to about 1920s or so. We came up with a new set of rules that we believed that the particles followed, and an entire new area of physics came out, which was called quantum mechanics. Okay, so now in quantum mechanics, the one of the concepts that is hidden, that is fundamental to quantum mechanics, is that when you talk of a particle, what you are actually talking of is the probability that the particle exists at a particular point. Okay, so when you make some diagram and you say a particle is at a particular point, what you are actually saying is that there is a high probability that the particle is at that point. That it is very important to understand that saying something is highly probable is very different from saying that it is certain. Okay, so that is the difference. So we have the concept of certainty and probability. Okay, what we are saying is, in classical approach of dealing with a matter, there is a certainty that something is somewhere. Okay, so any particle that I am talking of, no matter what size, scale, whatever, the moment I say that it is a classical particle, I am saying that I can say with certainty where that particle is. I am able to follow the particle, do a lot of things with respect to that specific particle. The moment I say that in fact the particle is behaving more like a quantum mechanical particle, then what we are talking of is that we are unable to say with certainty that the particle is at a particular location. We are only able to say that there is a high probability that the particle is at that location. Okay, so now why is this important to us? This is important because now when you have two trajectories, right, so I have a particle here and a particle here, it moves this way, this moves that way, they strike here, right. So I will just say there is one here and one here now at this point, and they bounce off. So let us say we have this situation, this is T0, this is T1, this is T2 time scales. Okay, so at T0 they are at two positions, they are moving towards each other, they strike each other at T1 and then they go to T2, right. So classical mechanics says that we can say with certainty that this particle is here, we can say with certainty it is up here, we can say with certainty it is up there, we can say with certainty the second particle is here, it is second particle is here and second particle is here. Quantum mechanics says that we only are able to say that there is a high probability that this particle is here. In fact, in quantum mechanics we use wave functions and so on, and the wave functions eventually represent probabilities that will lead us to probabilities of the existence of a particle at a location. So there is a high probability the particle is here, there is a high probability the particle is here, there is a high probability that they are here, and similarly there is a high probability that they are here. But the fact that it is not a certainty actually creates a situation that when you say that there is a high probability that a particle is here and a particle is here, there is a definite non-zero probability that they actually got interchanged. Okay, in classical physics that is not allowed. So when you have when we look at our example that we have two when we go back to this example that we have two orange balls, they come and they strike and they go out, right. In classical physics there is no question of a confusion of which ball ended up where. So they started here, they hit each other, they went out, there is no confusion, whichever ball is in my right hand remains there. In quantum physics we are saying that the particle only has a certain probability that it will be there. So when you go through this process, there is a non-zero probability that somewhere in this process they actually interchanged, and you had no idea when that happened, you had no control on the process. Okay, so you would still have two particles arrive like this, you will still have two particles sitting at those two positions, but you have no way of saying that what started out in your right hand has shown up on this side. You have no way of saying that this is actually the correct situation as opposed to this. What you will see is there are two particles at those two positions, that is all you will see. You have no way of knowing that in fact specifically the one that was on your right hand ended up on the right side and the one that was on your left hand ended up on your left side. Okay, so your inability to so what we find is that when you apply the rules of quantum mechanics, since there is only a certain probability that a particle could be somewhere, and therefore there is always a probability that if you have two different particles, you have two particles which are actually identical in the sense that their charge is the same, their mass is the same, their size is the same, everything else is the same, there is always a non-zero probability that at any given instant they have swapped positions. Okay, so there is a non-zero probability that this swapping could have occurred. Therefore, in addition to being identical particles, if you say that a set of particles follow quantum mechanical rules, we also additionally say that they are indistinguishable. Okay, so when we apply the rules of quantum mechanics, we are saying that particles are especially applied to a set of electrons, okay, which are inherently identical particles. We are additionally saying that not only are these particles identical, we are unable to distinguish between them because at any given point they could anyway be swapping with respect to each other. In classical mechanics, we are saying that even if they are a bunch of identical particles, the possibility of swapping does not exist because there is a certainty that it is here and a certainty that it is here, so they are always distinguishable. Okay, so so this is the difference. So quantum mechanics talks of identical and indistinguishable. These are identical but distinguishable. Okay, so classical particles are identical and distinguishable. Quantum mechanical particles, simply because they are talk of probabilities of a particle being present somewhere, are identical and indistinguishable. Why is this important? So it is important because if you have two energy levels, E1 and let us say E0, and I have a particle here and I have a particle here, in the classical way of viewing it, if I swap these particles, that is a new possibility, there is a new arrangement. In quantum mechanical way of looking at it, if you swap these particles, you do not get a new arrangement because they might have swapped anyway, in the sense you have no control on this. Even all you can say is there happens to be a particle up there and a particle down here, you have no idea which particle is down here, you have no idea which particle is up there. Okay, and the reason this is important is because this totally changes the way in which you count the number of so the way in which you count the number of microstates becomes completely different based on your assumption of whether or not it is classical or quantum. Okay, so this is the critical step at which the derivation of say the Maxwell-Boltzmann statistic will have to be changed when you try and create a new statistic which is valid for quantum mechanical particles. Okay, so what I wish to highlight is that this will change the way in which you the assumption of an identical and distinguishable particle which is valid for classical particles creates a certain way in which you can count your microstates, and therefore has a direct impact in the statistic that comes out of it, and therefore has a direct impact in how particles are distributed at various energy levels, and therefore how the specific heat of that system behaves. Whereas when you talk of particles which are obeying the quantum mechanical rules, they are identical but indistinguishable particles, and as a result the way in which you count those microstates becomes completely different, and because that becomes different, the final distribution that you get corresponding to quantum mechanical particles becomes completely different with respect to classical particles, and again that has a direct impact on the manner in which that system behaves with respect to energy, and therefore the manner in which it behaves with respect to specific heat. Okay, so this is where these distinguished characteristics begin to appear, and we have only briefly mentioned that that there is such a thing as quantum mechanics, and it came up in the year around the year 1900. In the next couple of classes we will spend a great amount of time specifically examining this idea of quantum mechanics, how it has come about, what are the fundamental ideas of quantum mechanics, why is it that people have had so much difficulty in trying to understand quantum mechanics and get a grasp of what it is that quantum mechanics is trying to tell us. I must also point out that in all of this the idea goes back to something that I have stated all along. Up front we do not know whether a particle is whether it is appropriate to say that a certain particle is a quantum mechanical particle or it is a classical particle. Okay, all we can do is we can only assume that something happens to be behaving in a quantum mechanical way or happens to be behaving in a classical way. Based on the assumption we derive a certain expectation of how that system should behave. If in fact the experimental data matches that prediction, then our assumption is right. So for example, when we talk of particles which are atoms of an ideal gas, okay, so the size scale is 10 power minus 10 meters. In that size scale those atoms are also a whole set of large collection of particles in a container. It turns out that if you make the assumption that they are classical particles, if you make the assumption that they are identical but distinguishable and therefore employ the Maxwell-Boltzmann statistics, then the behavior you get for those particles exactly matches the behavior that we can measure experimentally. Therefore it is fair and reasonable to say that those particles behave like classical particles. In fact all the even larger scale objects that we deal with in our day to day life will all fall in that pattern. If you go to the size scale of electrons, we find that the classical mechanical rules and Maxwell-Boltzmann statistics are not predicting their behavior correctly. So whatever property we are measuring of the material which we attribute to electrons is not getting accurately measured, is coming out to be a number very different from what the theory is predicting. On the other hand, if we just assume upfront without any prejudice, we just assume upfront that this may be a quantum mechanical particle, that maybe it is identical and also indistinguishable. If you make such an assumption, the kind of statistic that comes out of it, the kind of equations that come out of it will predict a certain behavior for a collection of electrons. It turns out that when you do it that way, the prediction actually matches the experimental values that we get. As a result, we can now, in hindsight, we can say that therefore it is correct that our assumption that it is a certain kind of a behavior for electrons is actually correct. So it is only in this process that we are able to say that certain such particle behaves in a quantum mechanical way, or rather the quantum mechanical effects are very significant for such a particle and are insignificant for atoms. They are very significant for electrons and very insignificant for atoms and such particles, and so that is the manner in which we utilize this. So what we will do in the next, so that is the thing. So we do not know upfront, we make the assumption and then we see whether or not we are right, and in this case and this is the difference between the two systems that we might follow. So what we will do in the next couple of classes is we will look at the history of quantum mechanics in great detail and try to examine how it has evolved, and then in the subsequent classes we will derive, I have just shown you that the microstates can be counted very differently if you put in the rules slightly differently, right. So we will actually derive another set of another statistical distribution which applies exclusively which applies very well to electrons in a solid, okay, and that would employ all the quantum mechanical rules. So what we will discuss in the next couple of classes will all get in addition to this fundamental idea that those particles are now identical and indistinguishable, all of those ideas will be put together in the next statistical distribution that we will derive, which incidentally would be called the Fermi-Dirac statistics, acknowledging the people who contributed to the creation of that statistical distribution. So we will put all that together 3 classes from now and create and look at the derivation of the Fermi-Dirac statistics, and that would then be employed to the electrons in a solid, and we will find that we will see at that stage, we will examine again and see how well that statistical distribution is predicting the properties with respect to what we get experimentally, and we will also examine in what ways even if it has in addition to the fact of identifying in what places it has succeeded, we will try to compare it back with the Maxwell-Boltzmann statistic and see in what form it has accommodated for the errors of the Maxwell-Boltzmann statistics. So this is what we will do in the next 3 classes or so. So with that we will halt for today. Okay, thank you.